Okay, everybody, this is your Chapter 13 video, and the title of this chapter is Chemical Kinetics, Cleaning the Air. Your book focuses on air pollution, so which is good. It makes it somewhat interesting to read, so please take time to read it. And what is chemical kinetics? Well, it's really just rates of reactions or the speeds of reaction, how fast they go. So it's really, just quantifying that, and we'll be able to basically rate laws, rate expressions, something like the rate is equal to some sort of rate constant times the concentration of a reacting species raised to some sort of power to actually describe the rate. And this becomes useful because now you can potentially, at a given concentration of A, you can predict the rate, or since you know the rate at any moment in time, you can determine the concentration of A. So for instance, if you have a pesticide spill in a river and you know the rate at which it decays, you can actually now figure out how long it'll take before that pesticide drops below some sort of toxic level. And you can also figure out, if you know the rate of the stream movement, how far downstream that will be. In the body, you can determine how long it's going to take for a particular chemical to, decay to the point where it's no longer detectable in the body. That becomes important in terms of medical treatment. If we do something like a chemotherapy drug or radiation treatment, we want to know how long it's going to be in the body, things like this. So we'll be able to look at something called half-lives also, which is the time it takes for half the substance to disappear, or to change into something else, I should say. Better wording. And we'll also look at mechanisms. And the reason we do this there's rate laws and mechanisms to get at what's happening on a molecular level. The kinetics can help us explain rates, but the rates can help us get to what's happening on a molecular level. So we'll model them in different ways. And that becomes really important. And one thing we'll focus on in this chapter is first order. And order doesn't mean anything to you right now, but first order reactions. There's different order reactions. There's zero order, first order, second order. We're going to focus on those in terms of calculations. So almost all our calculations will be based on first order. Your book will cover things like second order and zero order and do calculations with them. You'll need to know those graphically and need to know what the equations are and what they mean, but you're not going to have to do calculations with those. So that's important to realize. When you think about factors affecting rates, well, you should obviously know, some of these. Certainly temperature should jump into mind for you, is what affects the rate of a reaction. Temperature affects everything, and it's always on everybody's list when you're talking about that. The state of the reactants. If they're gases, solids, or liquids, right? The concentration of the reactants. Thing called catalyst, which you all probably know what those are. They're substances that speed up reactions without being consumed. So they can speed up another reaction and go and speed another one. The one you might not know is surface area. It could speed up a reaction. More surface area available for the reactants to come into contact. Because remember, for a reaction to happen, the particles have to collide or come together, right? It's easy to think about gases, but the same thing is the case with liquids and solids. And if it's a heterogeneous system, a gas reacting with a solid, that reaction of the gas has to come in contact with the solid. If the solid has a large surface area, that's going to speed up the rate. Okay, so they have to come into contact by collision, and those collisions have to be oriented in just the right way with the right amount of energy for the reaction to be successful. Just because a collision happens doesn't mean it forms product. Your book starts out with relative reaction rates. And this is important to understand, but I think they spend a little bit too much time on it and maybe make it a little bit more confusing than it needs to be. So when we talk about the rate of this reaction, we're talking about how fast the reaction goes. Okay? Now keep in mind, because of stoichiometric coefficients, it's very clear that 2NO form for every 1 N2 that disappears. So the rate at which NO forms is twice as fast as the rate at which N2 disappears. And really, the rate of the reaction is the overall reaction. So, that rate will equal, in this case, negative the rate of N2, because N2 is disappearing, which is equal to negative the rate of change, delta meaning change, of O2, which is equal to 1/2 positive because this is forming. So these are relative rates comparing the different reactant species. Your rates will be reported in things like molarity per second. And you can look at each individual component, but that's the rate of the overall reaction. When you want to look at individual ones, well then, the relationship of this to the overall reaction is 1/2. So the rate is 1/2 of NO. And a lot of people want to say 2. 2 change in concentration of NO over delta T is equal to, -1 of this. No, you're making them equal, so we need to take half of this since this is double the rate of formation. So to make it equal, it'll be half of this. And that's really all I need to say. Just think about this a little bit. To me, it's somewhat intuitive, and to spend too much time on it arises maybe too many questions and you overthink it, okay? So if NO forms at twice the rate in this reaction as the overall reaction, then we have to take 1/2 of it to equal the rate, or 1/2 of it to equal the negative rate of N2 or O2, something like that. Now, we'll see the actual reaction rates. These are actual numbers here for this particular reaction. This is N2 reacting with O2 to form 2NO. This happens in your combustion engine. High temperatures, the nitrogen from the air comes into your combustion chamber, right? Your air intake reacts with oxygen at high temperature, form NO. This is a pollutant. It goes on to react and form NO2, which is also a pollutant. But this reaction only occurs at high temperature. If it occurred at lower temperatures, we'd have a problem because it'd be happening in the air all around us because there's plenty of nitrogen and oxygen in the air. So you're looking at actual rates here, and you can see, of course, that looking at each time period, that within a given time period, the change in N2 and O2 is the same. It goes from, what do we start? Some 17 down to 13. So that's what? 3.9, right? And this is double, 7.8. So this is increasing to 7.8 in that same time period, right? Because it's forming at twice the rate. These are actual rates. So I just wanted to show you this so you're comfortable with the idea and looking at some real data. Now, this shows reaction rates. And what I want to show here is this is reaction rates. Actually, this is the way the slide is. Let's start with concentration here. This is concentration. So what happens at equilibrium, the concentration of the reactants, which is of course decreasing, stops changing. The concentration of the products, which is increasing, stops changing. And now we're at equilibrium when we reach about this point, say 3.5 minutes, if that's minutes. If this was rates, it would look like this. The rates have to be equal. So we're going to say this starts here. Oh, what the heck is that? That's weird. Okay, let's erase that. So let's take a look at the rate now. And the rate of the reactant should come down and go like this. And the rate of the products will start and go like this. And eventually the rates are the same. So when you're graphing rates, they will equal the same. When you're graphing concentration, they don't have to equal the same. In fact, that would be an unusual circumstance. Could certainly happen, but it's not the norm. Okay, now initial rates. Now you can talk about average and instantaneous rates. Average, is, I've driven to Nashville. My average speed is 70 miles an hour. My instantaneous rate at any given time will be greater than or less than 70. And there might be some cases where it's exactly 70. So the instantaneous rate is the tangent to the line. So we're not going to cover calculus here. You're not required to know it. But if you know your calculus or the tangent to the line at any given point will give you that instantaneous rate. An initial rate is just the instantaneous rate at time t equals 0. That's all initial rate is. It's the instantaneous rate at time 0. That'll be important because we'll look at initial rate data. We'll use that as a way to get information um, about certain reactions and what order they are. So that's where I want to talk about now. What is reaction order? What's the rate constant? Okay, so we can write a rate law, and that's what I did at the very beginning. And it's an equation that defines the experimentally determined relationship between the reactant concentrations and the rate of the reaction. So let's just say we have A plus B going to C. This might be a rate law. The rate is equal to the rate constant times A times B squared. Okay? The order, which is these up here, these are the orders, are experimentally determined. And it's determined by looking at how the rate depends on the change in concentration. So we'll do multiple experiments. We'll change the concentration of A. We'll keep B constant and see what happens to the rate. That will allow us to get to the order, which is your exponent. And you'll see that as we do that in class. And then you do the experiment the other way with B varying and A staying constant. The overall reaction order was just going to be, if these are N and M, the overall is just a sum of those. This is the individual order with respect to A. This is the individual order with respect to B. This would be the overall order. So what we're doing here is we're mathematically describing the rate of the reaction so that we can use this equation then to make predictions like I mentioned earlier. Because now if you know the concentrations, you can predict the rate. Of course, this will have to eventually be determined. Or vice versa, if you know the rate, you can predict the concentrations. And the rate constant is just a proportionality constant that relates these two together. You remember this term I used it in Gen Chem 1, fudge factor. That's a non-scientific term. It's a proportionality constant. It allows things to come out to the right magnitude and the right units. It doesn't change anything. It's just allowing us. We did this with gas laws. R is a fudge factor. It's a constant that allows the units to work out. So if I do a bunch of calculations for pressure, I'm going to get pressure units, and I'm going to get the right pressure that would be measured with a manometer based on the given temperature, number of moles of gas, and the volume. That's what a fudge factor allows us to do. So how can we determine rate laws? Well, we'll do this pretty much in class and spend time on this with initial rates, but I want to start by asking you this question. How do I determine the relationship between each reactant and the reaction rate? Well, so for instance, by holding these two constant and changing this, then I know that whatever changes here in the rate there are due to oxygen. So this is the way you set up anything experimentally. I try to teach my students this. When you're designing experiments, you only want to vary one thing if you can help it. Keep everything else constant so you know that the effect you see is a result of that particular parameter that you're changing. Keep all your other variables constant. Okay, then we look down here. We have these two that are held constant. So I can look at when this changes to that, what happens to the rate. So basically, we can use different trials. And when you actually design an experiment, you do this intentionally. But of course, those have been done for us. And now we can use those effects to actually determine how the rate depends on each of the concentrations. And that's kind of the nature of what a big chunk of the chapter goes on forward is the effect of concentration on reaction rates. So here's one where ozone reacts with nitric oxide to form oxygen gas and nitrogen dioxide. And there's the rate law. And it's dependent on ozone and nitric oxide. So it just means that increasing the concentration of either of those or both of them increases collisions between the reactants, leading to formation of products at a greater rate. So if I increase the concentration, I will indeed increase the rate of the reaction. You can see that because the rate is dependent on the concentrations mathematically. I want to talk about half-life, and we're only going to talk about first order. Half-life is talked about in your book pertaining to second order also, and I believe zero order. You only have to worry about it in terms of first order. And we'll derive this in class. To worry about it right now is to simply say for the half-life for a given species, and it looks like the half-life here is 1 second for this particular reaction, for N2O to decay to N2 and O2, every second, half of it disappears. So we go from 16 molecules down to 8. Now we're going to take half of that 8 and go to 4 in the next second. That's what half-life is, which tells you that less and less is consumed in each time interval. So the first step, you're consuming 8, the second step, 4, the third step, 2, and you get the idea. This is why this can stretch out a really long time, half-life, because it's half each time and it's half of the preceding amount. So after 3 half-lives, so you got half. After 3 half-lives, you have 1/8. After 1, it's a half. After another half, it's a quarter. Another half, it's an eighth. And that's the way it works with half-life. And we'll deal with that in class quite a bit. Factors affecting rate, of course, we said is temperature. And temperature increases the kinetic energy of the molecules and therefore increases the number of collisions, but also increases the energy of the collision. So it's a twofold effect to get more successful or faster rate, more successful collisions, because more of the collisions now have enough energy to get over this energy barrier here. This is an energy barrier to get things going. It's called the activation energy, kind of pushing that car to the top of the hill so we can get going down the hill. But increasing the temperature increases the number of collisions too, so there's a greater percentage then of a successful collisions. And if the forward reaction has a small energy of activation, well then the reverse reaction will have a larger one, because here's the energy of activation of the reverse reaction. And this is just showing you 3 different energy of activations or activation energies. So temperature will clearly affect rates of reactions. As the temperature increases, the fraction of collisions exceeding this minimum energy also increases, leading to an increase in K and an increase in the rate of reaction. So it's important to realize in this case, your rate constant will actually change. And we'll see that later on in the semester too. Some of these constants are dependent on temperature. The rate constant will not change. It's a constant, will not change with concentration. The rate will change, but not the rate constant. The rate constant is fixed. It doesn't matter about the concentration of the reactants and the products or any of that for a particular reaction. But it is affected by temperature, because the temperature can affect the energy of activation, and that changes potentially what's really happening in the reaction. It doesn't actually affect the energy of activation, it affects the number of molecules with enough energy to get over that energy of activation. So the rate constant actually is affected by temperature. So the fraction of molecules in a sample with enough energy changes as the temperature increases. And we'll look at this Arrhenius equation a little bit closer when we get to the lectures. The last thing is this energy profile for ozone decomposition. And all I want to do here is to show that what a catalyst does. And what a catalyst does, and it does it several different ways, and we'll talk about this in class, but it lowers the energy of activation. So this is a particular reaction in which is kind of a 2-step type of a reaction. So we have the ozone molecule that needs to be broken up, and then we need to have the formation of O2 in that process. So we got this kind of like 2 stages, if you will, and they have these energies of activations. Well, a catalyst lowers the energy of activation, makes it much easier to get over that hump, and therefore speeds up the reaction. A homogeneous catalyst is a catalyst that's in the same phase as the reacting species. In this case, and we'll talk about this with chlorine and ozone depletion and all of that. If they're both gases, then that's a homogeneous catalyst. Your catalytic converter is a heterogeneous catalyst. It's a solid matrix that's the catalyst, and the gases from your combustion engine get catalyzed. So that's a heterogeneous catalyst. And with that, that concludes our video for kinetics and chapter 13.